we're going to move on to part 2 of our final exam review, and we're going to look at chapters 12, 14, and 18 to wrap this up. Chapter 12 is on chemical bonding and molecular shapes, and let's start off with distinguishing between ionic, metallic, and covalent bonds. Those are the three basic bond types, and when we look at this categorization, we first recognize that ionic bonds are between a metal and a nonmetal. A metallic bond is between two metals, and a covalent bond is between two nonmetals. With an ionic bond, the metal gives away its electrons to the nonmetal, and you have a cation and an anion resulting from that electron transfer. That's the key phrase to an ionic bond. The electron transfers from the metal to the nonmetal. With a metallic bond, you have atoms that are very deficient in valence electrons, and the few electrons that they have are loosely held. They flow around the nuclei in what we call the electron sea. Because of this, metals are conductive by nature. With nonmetals, you have small atoms. These are on the right-hand side of the periodic table, where atoms are small, but they also have a lot of protons in the nucleus. And the effect is that nonmetals are very good at holding on to electrons. So these are tightly held, and what we find is that the covalent bond is characterized by nonmetal atoms which overlap their electron clouds and tightly hold electrons between the nuclei. We call it electron sharing by electron cloud overlap. You should be able to identify a compound and the types of bonds it would have, and this leads to physical properties. So let's look at a few different compounds, and you can help to determine the type of bond it would have. We would then say if it has ionic bonds, it would have high melting point, high boiling point, would dissolve in water. Covalent bonds would be low melters, and metallic bonds which would be conductive of heat and electricity. All right, here are some compounds for you. Let's look at carbon dioxide. Hopefully you categorize this as a covalent because you have a nonmetal and a nonmetal. Here's a metal with a nonmetal, K2O, potassium oxide. That's ionic. Then you see lead carbonate. Carbonate is a polyatomic ion. Lead sulfide ionic. Here we have sulfur with 4 hydrogens. This is all covalent. Now, hydrogen's an anomaly. It sits in both the metal and nonmetal category, but when it's with a covalent compound, when it's with a nonmetal, it's functioning as a nonmetal. This is covalent. And here we have metal-metal, so this is a metal alloy. Let's go through and assign polarity of a bond using the electronegativity values. Now, you do not have an electronegativity table on your resources guide, and so you would be given electronegativity values to calculate any type of polarity value. So if you look at if you would be given carbon's value of 2.5 and oxygen's value of 3.5, you would see that they differ by 1.0. So polarity is assigned on a continuum, and these are the basic cutoffs. If the electronegativity values of the atoms exceed 2.0, we call these compounds ionic. And if the electronegativity values differ by less than 0.4, we call these guys nonpolar. And in the middle are the polar compounds. So considering this CO2 as a difference of 1.0, we would call it polar, but then that would be for the bond, but the overall molecule ends up being nonpolar because of symmetry factors. So the CO bonds are polar, but the overall molecule is nonpolar due to symmetry. For K2O, potassium has a polarity has an electronegativity value of 0.8 versus oxygen's 3.5. So we would definitely call this ionic. Here's an ionic compound. We already classify them as ionic. Let's look at SH4 and see if this is a polar or nonpolar covalent. Sulfur has an electronegativity value of 2.5, and that happens to be the same. Well, hydrogen's a 2.1, so we would call this nonpolar. And then we wouldn't assign polarity on a metallic compound either. Okay, so polarity is a covalent compound thing. So we have done this, and this is basically the same thing. We've done this, we've done this. All right, let's refresh our screen and look at the sizes of atoms versus their ions. When we have a chlorine atom, it has 7 valence electrons. It sits in column 7, so you know it has 7 in the outer shell. They are, it finishes with 3s2, 3p5. That's a chlorine atom. Chloride ion has picked up 1 extra electron to achieve the octet, and we have a way of indicating that with Lewis structures. We use a bracket and we put the extra charge out here, and this has achieved the noble gas configuration of 3s2, 3p6. It also has 1s2, 2s2, 2p6 preceding. And so looking down below, which of the following ions is isoelectronic with, we find that this configuration of 1s2, 2s2, 2p6, 3s2, 3p6 is isoelectronic with argon. And so by chlorine picking up 1 electron, it achieves this same stability of argon. It's not argon because, remember, argon has 1 more proton in the nucleus than chlorine. One more example of this, let's look at sodium. Okay, sodium has only 1 valence electron, sits like that. This has the electron configuration of 1s2, 2s2, 2p6, 3s1. Being a metal, it achieves stability by giving away that 1 electron and crossing that out. And so we have 1s2, 2s2, 2p6. So the isoelectronic question for sodium, what noble gas would sodium ion be isoelectronic with? It would be isoelectronic with neon. So when you get this question about isoelectronic, be thinking about noble gases. Atoms gain or lose electrons to achieve noble gas stability. Look for the noble gas that it becomes. Last comments with Chapter 12. You do not need to draw any electron dot formulas, but you need to, in effect, to answer the question. So you'll be asked questions like, how many lone pairs are in an oxygen molecule? All right, so let's look at a couple examples. If I give you SH2 and ask you how many lone pairs are here, you need to work this through. So sulfur has 6 valence electrons, and hydrogen comes in with its 1. So we would see this as sulfur having 4 electron regions around it, but only 2 atoms bonded. So on the shapes table, it's a 4-2, which is bent. Or if you were asked the question of how many lone pairs, you would say 2 lone pairs. One more example. Let's consider PBr3. We put the least electronegative atom in the center. That'd be phosphorus. Phosphorus has 5 valence electrons. It sits in column 5. Bromines come along with their 7, so it would share first up, and then you'd have the 6 surrounding. So if you were asked shape, you would say there are 4 electron regions around the central atom and 3 bonded atoms, so you would say this is a pyramid. If you were asked the question how many lone pairs are around the central atom, you would say 1. Let's move on to chapter 14, acids and bases. Alright, you really should commit to memory, and I actually should put this on the memorization list. Here are your strong acids. You have nitric, sulfuric, HCl, HBr, HI, not HF, and perchloric and chloric. Alright, let's start chapter 14, acids and bases. Distinguish between strong and weak acids. First of all, strong acids by definition ionize 100%. By that we mean when this acid is put into water, it completely breaks up into H plus and the other thing. We'll just call it A minus. Okay? Likewise, strong bases completely ionize into OH minus and the other thing. There was some cation part of it. So what are the strong acids? Let's just memorize these 7 strong acids. The number 1 strongest acid of all is perchloric. And then take away an oxygen and you get chloric. Then you should memorize nitric, sulfuric, and this series with the halogens, HCl, HBr, HI. Not HF. Okay, HF is a weak acid. If you memorize that, then you can distinguish. Alright, the strong bases, column 1 metals with OH minus. So we're talking NaOH, LiOH, etc. The column 2 metals might be strong bases also. Alright, which of the following would strongly conduct electricity? By that we mean ionize 100%, which is just asking which of these are strong. Is acetic acid on the list above? No. Is ammonia a strong base? No, just column 1 metals with hydroxide. Is HCl on the list? Yes. Is NaOH on the list? Yes. Is HNO3 on the list? Yes. So memorize these 7 strong acids, know that column 1 metals with hydroxide form strong bases, and you're all set for these questions. Now we have a number of calculations for pH. Be very proficient on your calculator going back and forth on pHs and figuring out the hydrogen ion and hydroxide ion concentrations. Alright, what is the hydroxide concentration in an ammonia solution if the pH is 8.20? Alright, I can tell you right away you're going to have 2 steps, because when I reverse this pH 8.2, I will get the H plus concentration. It's going to be 10 to the minus pH. But I'm asked for the hydroxide, so I'm going to have to use a second relationship to get that. Well, anyway, let's get the H plus first. It's this. It's 10 to the minus 8.2. On your calculator, you could either do inverse log, or you could just go 10 raised to the negative 8.2. Make sure you use the change sign and not the subtract key to insert that negative. and you get 6.3 times 10 to the minus 9 molar. You know that's good because this 9 is similar to the 8.2. That's what logs are all about. They help simplify powers of 10. And you should always have an agreement when you reverse this 8.2 into its molarity equivalent. They should be very similar. All right? Now, how do I get hydroxide if I know H+? There's a relationship that you need to finish this problem, and that is the fact that in water, the hydrogen ion concentration times the hydroxide concentration is always 10 to the minus 14. It's a constant. This is called the autoprotolysis of water. That said, I just figured out what H+ is. We just figured out that it's 6.3 times 10 to the minus 9. So I have one unknown in this problem. My hydroxide concentration will be 10 to the minus 14 divided by 6.3 times 10 to the minus 9. And when I do that, I get 1.6 times 10 to the minus 6 molar. Okay, molar is big M moles OH minus per liter. Alright, what is the pH if the H+ is this? Alright, so pH is minus the log of the H+. These relationships here are reciprocals. They're saying the same thing. In this problem, because I'm given the H+, I want to log it, and it will be a negative number, and I'll make it positive. pHs are positive. Okay, they're always positive. So minus the log of, and you're just going to put in your calculator the log of 6 zeros 1 5. Okay, when I do this, I should see something around a 6 or a 7. So I go log of, well, I don't put all those ones in. I would go 1.5 times 10 to the minus 7. And I'll get negative 6.8. And I make it positive. That's what the change sign is there in the front. Okay, 6.8. Next question, Bronsted-Lowry acids. Okay, this idea of Bronsted-Lowry acid, remember they are the H+ donors. And the Bronsted-Lowry base is the recipient of the H+. Okay, so you have to see what's happening over here. We see that this is actually phosphoric acid is reacting with water, and it's forming H2PO4 minus and H3O plus. Who's the donor here? This guy. This guy's the donor. It gives away its proton. See how that transferred the proton to the H2O? We would say the H2O is the Bronsted-Lowry base, and this is the Bronsted-Lowry acid. The last question is a titration problem question. All right, we've got an acid. The last question is a titration problem question. What is the molarity of an acid if 50 mils of it is neutralized by 27.5 mils of 0.15 molar NaOH? So go to your titration equation. MaVa equals MB BB, and I'm looking for MA. That's my desired thing. I know VA is 50. You don't have to switch to liters if you're consistent and you keep milliliters on both sides. Molarity of base is given as 0.15, and the volume of base is 27.5. So we're going to solve for molarity of the acid, and we get 0.15 times 27.5 divided by 50. 0.0825. And being consistent on sig figs, we get 3. So we'll say it's 0.083 molar. That's it for Chapter 14. Let's move on to Chapter 18, our last chapter on radiation. What is a radioactive isotope? We're saying the nucleus is unstable and decays, cleaving off particles such as the alpha, beta, gamma positron. You should know all of these particles, okay? So the alpha symbol is 2 protons, 2 neutrons for a 4-2. This has a 2+ charge. It's the most massive of all the particles, and it's, because it's massive, it's slower. Alright, let's move on to our last chapter on nuclear chemistry. First of all, what's a radioactive isotope? Isotope's a particular atom specifying its protons and neutrons. If it's radioactive, the nucleus is decaying, and it's cleaving off these particles such as the alpha, beta, gamma positron. You need to know these particles. The alpha particle is the most massive. It's got 2 protons and two neutrons. It's got a 2+ charge, and it is the least penetrating, okay? So it can't make it through paper. Paper will stop an alpha particle. However, if you ingest it, it is destructive because it's heavier and it can cause more damage in your cells. Next up is the beta particle. The beta particle is the same thing as an electron, but we don't call it an electron because it's coming out of the nucleus. It's got a charge of a -1, and this can be stopped by aluminum foil, which would interact with the electron. And then you have the gamma particle, which is pure energy, no mass, no charge, and it has to be stopped by lead. The last particle I want you to know is the positron, which is given this symbol. It's the same as the electron, but it's antiparticle, so it's got a +1 charge, and it would be stopped by aluminum foil. All of these particles travel at the speed of light because they're radiation. Okay, we're at the high end of the electromagnetic spectrum, and they all travel at the speed of c. Be able to complete a nuclear decay reaction. Okay, this could come in any variety. Let's talk about the beta decay of uranium 238. If uranium, which has 92 protons, would undergo beta decay, it means on this side I need to have a beta particle, and you have to figure out what is this other thing. Well, for my math to work out, remember the bottoms and the tops have to be equal on the left and right of the reaction equation of the reaction arrow. I'd need a 93 down here, and I'd need a 238 up here. And so what's my missing element? You've got to look at your table and you see this is neptunium. That would finish that out. Okay, let's look at one more example. Let's say we have electron capture of thorium 232. The electron capture is the only one that happens on the left side of the arrow. If I have thorium with 90 protons specifying the mass of 232, if I capture an electron is just like a beta in that it's a -1, 0. What must the math be on the other side? It's got to be 89 down here, 232 up here. What is this element? It's actinium. So you need to be able to do nuclear decay reactions such as these. No, fission versus fusion. Conceptually, fission is where you have big atoms decaying. So this is where you'd have like the uranium breaking apart. Fusion's where you have, this would be like the hydrogen bomb. Where I have deuterium. Sorry, that's a 1. Deuterium combining with regular hydrogen to make okay, no fission versus fusion. Fission is where you have the big atoms splitting up. This is what we do for nuclear power, for instance. This is also the atomic bomb. You have the U-238 and it breaks down over time and releases a lot of energy that way. Fusion is the hydrogen bomb. It's where you take small ones, combine small atoms, you fuse them together, and on the right I have this image of the deuterium atom and the tritium atom, which are two isotopes of hydrogen, colliding in the hydrogen bomb to produce, releasing a neutron and a helium atom and much energy. Alright, what does a Geiger counter measure? Each time you hear a blip on the Geiger counter, that's a nucleus decay moment. Okay, you hear a particle coming off. Who discovered radiation? It was accidental. Henri Becquerel. He put the photographic films in his desk drawer while he went on vacation with some uranium or some other radioactive rocks, and he came back and he saw images on the photographic plates. What radionuclide decays to iron 56 by beta emission? Alright, beta emission means that the beta particle is on the right, and so is the iron 56. 56 is the mass, because from the periodic table you can get the atomic number for the bottom. And so on this nuclear decay reaction, we need a 25 on the left bottom, and we need a 56 on the top. You check out your periodic table, and you see that would be manganese, which would decompose in such a way. What is the approximate mass and relative charge of an alpha? We've already seen the alpha. It's a 2, 4. The mass is 4 AMUs, and the charge is a 2 plus, 2 protons. What particle is emitted when U-235, uranium has an atomic number of 92, decays to thorium? Thorium is 90. 231 is the mass. Well, what would be the particle? What is this missing thing? I need a 2 on the bottom. I need a 4 on the top. That would be an alpha. Last problem, half-lives. The key question you want to say to yourself whenever you have a half-life is, how many half-lives is that? We have radioactive I-131, has a half-life of 8 days. A hospital purchased 50 grams of I-131 on day 1. How many grams of I-131 remain after 24 days? Okay, so 24 is 3 sets of 8, or 3 half-lives. Okay, half-life 1 is 8 days, half-life 2 is 16 days, half-life 3 takes us to 24 days. Well, after the first half-life, how much would there be? There would be 25 grams at that time. Have it again, there'd be 12.5 grams. Have it again, after 24 days, you'd have 6.25 grams, or approximately 6 grams, of radioactive I-131 remaining. All the rest would have become stable. That's it. You've made it through the practice final. A few notes. Don't worry about heat calculations. Don't worry about coordinate covalent bonds. They're not on the final. If you have any questions, please ask me. Thank you for sticking with me through these 2 long videos. And I'm here to help you do well, so please don't be afraid to send me a question if you have anything that you're struggling with. Okay? Thanks again for your hard work through this semester. I've really appreciated getting to know you. Bye.